Okay, so we're going to look at now some of the properties of dot products, and I know you have them all in front of you, but we'll explain them as we go along, um, and I'll explain them one by one. But what we want to do here is just make sure that the rules for multiplication that we know when we're multiplying numbers, or the rules that we know when we're multiplying variables in algebra, we got to figure out which one of those apply and work for multiplication of vectors. And that's what these properties will examine. So the first one says that u dot v equals v dot u. So that means the order in which we multiply doesn't matter. And that should make sense. It makes sense for algebra. It makes sense for numbers. 5 times 2 is the same as 2 times 5. Also, if we were to write out these, if we wrote out the formula, magnitude of u, magnitude of v cos theta, for the first one, of course, that's going to equal the magnitude of v times the magnitude of u cos theta. When you multiply the u and the v numbers, they're going to be the same, and of course the angle between them are the same. So naturally, this is true. The second one talks about what happens when you have a scalar multiple. So in this case, the scalar multiple is some k value. So if you think back to the first day of vectors, we said if we had something like a vector u and then I asked you to draw 3u, it would just be a vector that is 3 times bigger. So when you have a scalar vector of 3, that 3 can actually be multiplied anywhere in this operation. You can imagine if I put a 3 in front of one of these, you can multiply the 3 with the u, or you can multiply the 3 with the v, or whatever. It doesn't matter where you multiply. And that's what this rule says here. So k is a scalar multiple. When we're taking the dot product, it doesn't matter if the scalar multiple goes with u, or if it goes with v, or if you took their dot product first, then multiplied it by k. It's a scalar multiple, and in multiplication, it doesn't matter if I'm multiplying where I multiply that 3 in, or that 4, or that whatever that scalar multiple is. Next. Hopefully you'll recognize this as actually kind of like rainbow. Here we have u dot v plus w. You know the rules for rainbow is that if you have something outside the brackets, it gets multiplied by each term inside the brackets. So the same thing applies here. U can be multiplied using the dot product with v, and then take the dot product of w. So there's u dot v, and since we're adding, we're going to add u dot w. This is just rainbow. So it's good to know that rainbow works not only for numbers, for algebra, but it also works for dot product of vector multiplication. Interesting to consider whether it works with the cross product later on. It may or may not be true, but for dot product of multiplication, it does. That's all we're worried about today. Next one. It says u dot u is actually just equal to the magnitude of u squared. And that's curious because usually when we have the dot product, we have an angle somewhere here, and the angle seems to be gone, or the cosine seems to be gone. But if we apply the formula, this is magnitude of u times itself, magnitude of u, cos theta. Well, what I ask you then is, what's the angle between u and itself? Well, the angle between is 0 degrees. If you have u and another u, and they have to be in the same direction, so the angle between them is 0. So now we're taking the magnitude of u times the magnitude of u cos 0. Oops, excuse me. Cos of 0, not theta. Cos of 0. So what's the cos of 0? Well, cos of 0 is 1. Where does cosine start? It starts at 1. So this is just a 1. This is just a 1. And this is magnitude of u times itself, so we can consider it being magnitude of u squared, which is what we have here. you don't actually need to use the formula there because the angle between them is 0 and it's just the cos of 0 is 1. So you can just square them if you're taking the dot product of two vectors by itself. This last one is an interesting statement. It's an IFF. You'll notice that it's written differently on your page. IFF is a biconditional statement. It means that it works in both directions. So instead of having to write it out twice, you'll see it written out just once. You'll see on your page, it actually I'm not sure if it's on your page or not, so I'll write it out both directions here. What this says is if U is perpendicular to V, then U dot V is 0. And the other direction is if U dot V is equal to 0, then U is perpendicular to V. Now, not all theorems are biconditional. They work in both directions. This one happens to. So the shortcut, instead of writing out both sides of this, is we do this if and only if. We put an IFF in between it. Now, that's not the important part. The important part is recognizing that if you have two vectors that are perpendicular to each other, their dot product must be 0. So that's curious as well, and I wonder why that is. Well, again, let's try their dot product. So magnitude of U, magnitude of V, cos theta. If we have two vectors that are perpendicular, then theta is equal to 90 degrees. And so what we end up doing is taking the magnitude of U times the magnitude of V of cos 90. Well, if you stop and think for a second, the cos of 90 is 0. You can check it on your calculator or think of the sketch. We know at 90 degrees the graph goes at 0. So this is 0, and it doesn't matter that I'm multiplying it by U and V, it's just 0. And so their dot product is 0. So it actually makes sense that if the two vectors are perpendicular, their dot products are 0. And then, of course, the other way around, if you do the dot product of two vectors and you find out that the answer is 0, then you can conclude that the vectors are perpendicular. This is an important idea, one that I'm going to refer to and ask you to think about later on, and it's amazing how many people forget this idea. I'm going to come along and say, I wonder if these two vectors are perpendicular. How could we find out? Well, the way we find out is take their dot product. If it's equal to 0, then you know they're perpendicular. Another word for perpendicular is orthogonal. You'll hear that word in some of either my lessons or in other video online lessons. So perpendicular and orthogonal mean the same thing. But those are the properties of the dot product.